Hello, welcome to another video. Today we're going to be talking about the second method of solving differential equations. So if the differential equation is not separable, then you're going to move to a method called integrating factor. So this is a first order linear method. And a first order linear differential equation has the form dy over dx plus some function p of x times y, the dependent variable, equals q of x. So if we have something that's in this form, it is not separable, then we have to use this method. And one of the things that we can do is we can identify, using an example, what p and q are. So I will give the example dy over dx. Example is plus 2 times y equals 6x. So we have the same form that we mentioned up here. Now we just identify p of x okay, and then we identify q of x. And now that we've done that, we can define something called the integrating factor. The integrating factor definition is denoted by mu of x, and it's equal to the exponential function of p of x dx. Well, we already determined that p of x equals 2, so we can just put that in there and integrate the argument of this exponential function to get e to the 2x. That is the integrating factor by which we will then multiply to this diff eq. We'll multiply the entire diff eq by this integrating factor. That's why it's called a factor. So I'm going to do that right now. So we have e to the 2x times dy over dx plus e to the 2x times 2y equals e to the 2x times 6x. Now there's something we have to realize about this. If I rewrite this in a simpler way, or in a way that we can see what I'm about to say, it will be better. So this right here, the left-hand side of this equation, collapses to the power rule because we have one function times the derivative of the other plus that function that we took the derivative of, that's y, times the derivative of this first term, this first function. And so really we can just recast this as the derivative with respect to x of the product of two different functions. And then on the right-hand side, 6x times e to the 2x remains. How do we get rid of this differential operator? We integrate. And so by integrating this, we basically the differential and the differential operator and the integration operator cancel each other, as we learned in calculus class. And then this integral right here, though, this is going to require integration by parts. But there's an easy way to do it called the tabular method, which I'm going to employ here. But I do suggest that you go through the other method as well. So what we do is we just take a table of our two functions in this integrand, And then we just start taking derivatives as we go down the rows. And we do that for both columns. And so now that we've got that, what we can do is basically assign the alternating signs, starting with the positive. So this will be positive, this will be negative, and then the other one doesn't matter. But then we're basically just going to multiply diagonally. So this is going to turn into 6x times 1/2 e to the 2x minus 6 times 1/4 e to the 2x. And so I'll just write that out real quick. So we have 6x times 1/2 e to the 2x minus 6 times 1/4 times e to the 2x. And don't forget your constant of integration. So that's the integration step. That's called the tabular method for integration by parts. So now what I can do is I can just, again, rewrite the equation, plugging in our evaluated integral, right? So we have, looks like 3 e to the 2x minus 3/2 e to the 2x. Ooh, I think I messed up somewhere. Yes, I did. This should be a 3x. Because there's an x here. And then minus 3/2 e to the 2x plus c. One more step, we've got to get y by itself. So if we actually just divide through by e to the 2x, well, this is going to cancel, that's going to cancel, but it's going to, we're going to keep this term in terms of e to the 2x, right? So I'm just going to write that out. We have 3x minus 3/2 plus c e to the negative 2x, right? That's the same as just dividing it by e to the positive 2x. It's just a nice touch, a way you can put your solution that looks nice. And so this is the function y that will solve this non-separable diff-EQ here. And so I hope this helps. I'm going to wrap the video up here, and just let me know in the comments if you need me to clarify anything. And also, if there's anything that you would like me to talk about in the future on future videos, also leave that in the comments. Don't forget to like and subscribe. Have a wonderful day.